Relativistic wave equation, expert level, part 1. Poveda-Poirier-Grave de Peralta equations. Let's talk first about the Klein-Gordon equation. The Klein-Gordon equation for a spin-zero particle with mass m in the central potential V is given by this expression. This is very well known. It has solution with total energy E plus mc2 and solution with total energy E prime minus mc2, where c is the speed of the light in vacuum and E sub t is the total energy of the relativistic quantum particle. The time-dependent Klein-Gordon equation is given by this expression. This is also very well known. By substituting the total energy by E plus mc2 in the time-dependent Klein-Gordon equation, and after some algebraic manipulation, we obtain the equation below. However, by substituting the total energy by E prime minus mc2, we obtain, in the Klein-Gordon equation, we obtain the equation below. Then these two equations are obtained from the time-dependent Klein-Gordon equation for the case that the energy is E plus mc2 or E prime minus mc2. These two equations will be used later. Schrodinger-like Poveda-Poirier-Grave de Peralta equations. There exists no one but two waves associated to a particle with mass larger than 0 and a spin 0. In one wave, the particle can have total energy E plus mc2. What wave equation this wave is a solution of? Well, is the Schrodinger-like PPGP equation given below. If you look at this equation and you substitute mu by the mass of the particle, this is the Schrodinger equation. But mu is the effective relativistic mass of the particle, is a local function on the position of the particle. The corresponding time-dependent equation is given below. Relativistic quantum particle have two waves associated to it. In one, the energy of the particle in the wave is E plus mc2. In the other one, that corresponds to the particle exotic state, the energy is E prime minus mc2. What wave equation this wave is a solution of? Well, it's a solution of the complementary Schrodinger-like PPGP equation shown below. It's very similar to the one above. The only difference is that the effective relativistic mass is different. It's given by a different expression. It's also a local function on the position of the particle. If E prime minus B is much smaller than mc2, this is a non-relativistic limit, the mu prime is equal to minus m, is a negative effective mass. These don't exist in non-relativistic quantum mechanics. The corresponding time-dependent equation is given below. Theorem 1, valid for particles with spin 0. This theorem relates the solution of the Klein-Gordon equation with the solution of the Schrodinger-like PPGP equations. Theorem number 1. By solving the Schrodinger-like PPGP equations, we obtain the exact solution Z and E and ρ and E prime of the Klein-Gordon equation with total energy E plus mc2 and E prime minus mc2, respectively. Demonstration. The equation below can be obtained from the Klein-Gordon equation for the case that the total energy of the particle is E plus mc2. It can also be obtained pre-multiplying by mu over m, both sides of the time-dependent Schrodinger-like PPGP equation, and then substituting mu by its value shown here. This is half of the demonstration. The equation this is the second equation that you can obtain from the Klein-Gordon equation when the energy of the relativistic quantum particle is E prime minus mc2. It can be obtained. It also can be obtained pre-multiplying by mu prime divided by m, both sides of the complementary time-dependent Schrodinger-like PPGP equation, and then substituting mu prime by this value in the expression below. This completes the demonstration. Again, this theorem shows that you can obtain the solution of the Klein-Gordon equation by solving the Schrodinger-like PPGP equations. Let's talk now about the Dirac equation. It is well known that the Dirac equation is the correct Lorentz covariant equation that describes the interaction of a spin 1/2 particle with mass m and charge E with the external electromagnetic field. The stationary solution of the Dirac equation are B spinors, which means they possess 4 components. They are of the form shown below. The solution of the Dirac equation are formed by 2 spinors. It also widely known that the time-dependent Dirac equation is equivalent to the following system of 2 coupled spinor equations, the equation shown below. In these equations, we have a operator sigma, that is a vector operator and is a matrix operator. The 3 components of the operator sigma are the well-known 2 by 2 Pauli matrices, and in this equation also E and E0 are the vector and scalar potentials of electromagnetism. Then let's obtain now the coupled equations from the set of 2 coupled equations. From the second coupled equation that we show in the slide before, follows the following equation. Substituting this in the first coupled equation, we obtain the equation below. This is the coupled equation. With this equation, we can obtain phi, the spinor phi. Alternative, from the first coupled equation follows the equation shown here. Substituting this in the second coupled equation, we obtain the equation below. This is the coupled equation that allows us to find phi. Pauli-like Poveda-Poirier-Grave de Peralta equations. There exists no one but 2 waves associated to a particle with mass larger than 0 and a spin 1/2. In one of these waves, the particle have energy E plus mc2. What wave equation this wave satisfy? Well, satisfy the Pauli-like PPGP equation showing here. You should see that the value of mu is the same value of mu that was used for the Schrodinger-like PPGP equation. Also, if mu is equal to the mass of the particle, this is the Pauli equation. The corresponding time-dependent equation is shown below. The particle can be in 2. There is 2 waves associated to a particle. One of them, the energy is E plus mc2. The another one corresponds to the particle exotic state with energy E prime minus mc2. What equation these particles exotic states are solution of? Well, the equation is the complementary Pauli-like PPGP equation that is shown below. It's basically the same one in the top, but changing mu by mu prime, the same mu prime that was used in the complementary Schrodinger-like PPGP equation. if this equation don't have analog in non-relativistic quantum mechanics. The corresponding time-dependent equation is shown below. Theorem 2, valid for particles with a spin 1/2. What is this theorem? This theorem relates the solutions of the Dirac equation with the solution of the Pauli-like Poveda-Poirier-Grave de Peralta equations. Theorem number 2. By solving the Pauli-like PPGP equation, we obtain the exact spinors and energies Z and E and ρ and E prime that correspond to the solution of the Dirac equation with total energy E plus mc2 and E prime minus mc2 respectively. Demonstration. Starting from this equation, this is one of the two decoupled equations that I obtained before, and doing the effective mass, the relativistic effective mass of the particle in this state equal to this expression, noting that E times E0 is the potential, and making the total energy equal to E plus mc2 follows that 1/2 times mu is given by the expression shown here, that is what is in the equation in the top, in the middle, in the left side of the equation. The time-dependent Pauli-like PPGP equation follows from the above equation, combined with the starting equation with E plus mc2. Alternatively, starting from another decoupled equation, I'm making mu prime equal to this expression, and noting that E times E0 is the potential, and making the total energy E prime minus mc2 follows that 1/2 prime mc2 is this expression here. Then the complementary time-dependent Pauli-like PPGP equation follows from the above equation combined with the starting equation with E prime total energy equal to E prime minus mc2. This completes the demonstration. Note: Theorem 2 refers to the calculation of the principal spinors and energies psi and E if the total energy is E plus mc2, and ρ and E prime if the total energy is E prime minus mc2. However, the solution of the Dirac equation are B spinors. After the principal spinors are known, the secondary spinors can be found as, and here you see the equation. These equations correspond to the coupled equations that are equivalent to the time-independent Dirac equation. Let's talk now about antiparticles. Antiparticles, assuming that the particle and the antiparticle interact with the same external world. The external world is the nucleus of a hydrogen-like atom producing the external Coulomb potential. The nucleus will have Z protons. When the particle, the electron, moves around this nucleus, results a hydrogen-like atom, and the electron is spatially localized around the nucleus. Alternatively, if it's the positron, the one that is moving around the same nucleus, positron moving around the nucleus of a hydrogen-like atom, the repulsion between the nucleus and the positron results in a state that is spatially delocalized. Antiparticles, Schrodinger-like PPGP equations. There is no one, but two waves associated to each antiparticle with mass larger than 0 and spin 0. The antiparticle can be in a wave with the particle energy E sub A plus mc2. What equation these waves is a solution of is the Schrodinger-like PPGP equation for the antiparticle that is shown below. How you get this equation? Well, the only thing that you have to do is to write the same equation for the particle and change B for minus B. The corresponding time-dependent equation is shown below. Like the particle, the antiparticle is associated to two waves. In one, the energy is E sub A plus mc2. In another one that corresponds to antiparticle exotic state, the energy is E prime sub A minus mc2. What wave equation this wave is a solution of? Well, the complementary Schrodinger-like PPGP equation for the antiparticle that is shown below. How you get this equation? Well, you get the complementary Schrodinger-like PPGP equation for the particle, and then you change B by minus B. And in both cases, you change B by minus B in the equations and in the expression for the effective relativistic mass of the antiparticle. The corresponding time-dependent equation is shown below. Antiparticles Pauli-like PPGP equations. There exists no one but two waves associated to each antiparticle with mass larger than 0 and spin 1/2. In one wave, the energy of the antiparticle is E sub A plus mc2. What wave equation this wave is a solution of? Well, it will be the Pauli-like PPGP equation for the antiparticle. How you obtain this equation? Well, you write the Pauli-like PPGP equation for the particle, and then you substitute B for minus B, and you substitute E times A divided by C for minus E times E divided by C. The corresponding time-independent equation is shown below. The antiparticle with the spin 1/2 can have energies E sub A plus mc2, or can be in an antiparticle exotic state with energy E prime sub A minus mc2. What equation this wave is a solution of? Well, it will be the complementary Pauli-like PPGP equation for the antiparticle. How you obtain this equation? Well, you write the complementary Pauli-like PPGP equation for the particle, and then you make the same substitution. The corresponding time-dependent equation is shown below. Theorem 3. The theorem 3 is a very interesting theorem. It relates the exotic state of the particle with the common state of the antiparticle, and also relate the exotic state of the antiparticle with the common state of the particle. Theorem 3. The particle wave equation that corresponds to the exotic state with energy E prime minus mc2 can be obtained from the antiparticle wave equation that corresponds to E sub A plus mc2. Also, the antiparticle wave equation that corresponds to the exotic state with energy E prime sub A minus mc2 can be obtained from the particle wave equation that corresponds to the energy E plus mc2. This theorem is valid for particles with spin 0 and is also valid for particles with spin 1/2. Therefore, we will start by giving the demonstration for particles with spin 0. That is simple. Demonstration for particles with spin 0. The complex conjugate of the antiparticle Schrodinger-like PPGP equation is the equation shown below. If in this equation we change E sub A for minus E prime in the expression for the effective relativistic mass of the antiparticle, we obtain the equation below. This equation is the particles complementary Schrodinger-like PPGP equation. Therefore, we have found a relation between exotic state of the particle and a common state of the antiparticle. The two wave functions corresponding to this state are related by a complex conjugate operation. Also, starting for the complex conjugated of the particle Schrodinger-like PPGP equation that is shown below, and making similar substitution, but now changing E, the energy of the particle, for minus E prime sub A, the energy of the exotic state of the antiparticle, and we made this change in the effective mass of the particle in the above equation, we obtain the equation below. This is the antiparticles complementary Schrodinger-like PPGP equation. Therefore, we obtain again a relation between the exotic state of the antiparticle and the common state of the particle. The wave function corresponding to this state are related through a complex conjugated operation. Demonstration for particles with a spin 1/2. Noting that the operator sigma in the Pauli equation is hermetic, the complex transpose conjugated of the antiparticles Pauli-like PPGP equation is the expression below. The symbol cross means the operation complex transpose conjugated. This equation can be rewritten in the form that is below. Then changing the energy of the antiparticle for minus E prime in the effective relativistic mass of the antiparticle in the above equation, we obtain the equation below with the expression for mu prime given by this expression. This is the particles complementary Pauli-like PPGP equation. Therefore, we have obtaining a relation between the exotic state for the particle and the common state for the antiparticle. They are related through the operation of complex transpose conjugate. Similarly, but starting from the complex transpose conjugated of the particles Pauli-like PPGP equation and changing E, the energy of the particle, for minus E prime sub A in the resulting equation, we obtain the antiparticles complementary Pauli-like PPGP equation. Therefore, there is also a relation between the exotic state of the antiparticle and the common state of the particle. The wave functions corresponding to this state are related through the operation of complex transpose conjugate. Let's see an application of theorem number 3, common particle and antiparticle state in a Coulomb potential. It is very well known that the electron quantum state with total energy E plus mc2 are spatially localized by external attractive Coulomb potential. The example is the hydrogen-like atom. The electron is confined around the positive nucleus, and consequently, the spectrum of energy is discrete. These are the common quantum states that in the non-relativistic limit are studied in non-relativistic quantum mechanics. These states are solutions of the Pauli-like PPGP equation shown below. It is also well known that the positron quantum state with total energy E sub I prime plus mc2 are spatially delocalized by the external repulsive Coulomb potential produced by a positive nucleus. The positron is repelled by a positive nucleus, and for this reason, these states are spatially delocalized. These are the common positron quantum state, and they are solutions of the Pauli-like PPGP equation for the antiparticle. If you compare the two equations, the only difference is that in one, the Coulomb potential is attractive. This means have a minus sign in the equation. And in the another one, the Coulomb potential is repulsive. This means have a plus in the equation. Now we can see how to use theorem 3 to find the exotic particle and antiparticle state in a Coulomb potential. First, we will see that the exotic electron quantum state with total energy E minus mc2 are spatially delocalized by external attractive Coulomb potential. This is shown here below. The exotic state of the electron in hydrogen-like atom are spatially delocalized. How we know this? Oh, because we know that the common positron state of a positron moving around the same nucleus are spatially delocalized due to the repulsion between the positron and the positive nucleus. And because there is a relation between the common positron states and the exotic electron state in the hydrogen-like atom. The relation between the wave function of this state is through the operation complex transpose conjugate. We also can see that the exotic positron quantum state with total energy E sub A prime minus mc2 are spatially localized by external repulsive Coulomb potential. How we know this? Because we know that there is a relationship between the wave function of the common state of the electron in the hydrogen-like atom and the wave function of the exotic positron state of a positron moving around the same nucleus. The electron state, the common electron state, are spatially localized, and then the positron exotic quantum state are also spatially localized. A very important thing here to remember for the future is that there are two spatially localized states due to a Coulomb potential. If the Coulomb potential is attractive, the particle common state are spatially localized. But if the Coulomb potential is repulsive, then the antiparticle exotic state are spatially localized. Curious? You should now be ready to watch the part 2 of the expert level video titled Antimatter. A rigorous presentation of these ideas can be found in the book titled Relativistic and Non-Relativistic Quantum Mechanics, both at once, authored by Luis Grave de Peralta and his collaborators, and published by Spring Nature in 2023. In this book, the Poveda-Poirier-Grave de Peralta equations are presented and discussed. These are the relativistic equations the book is based on. Thank you very much.